Okay, so the antiderivative. Now, the antiderivative, or also known as the primitive function, is basically just the opposite of differentiating. So we're going to give you the derivative, and what we want you to do is give us back the original function. So what would have we had to have differentiated to begin with? And so what we're going to do is we're going to look at how we can do that. But first we're going to start off by looking at an example like this. So what has happened is we've been given the derivative function. Okay, so this is describing what the function is doing in terms of its slopes. So left of x minus 1, the slope, it starts off very positive, okay, because this is in the positive section, and it slowly creeps down until it hits 0. So in other words, the function, it starts positive, and it starts really positive, and it goes up until it hits a point where it stops. Then once it does that, it starts becoming negative again. It keeps being negative, and this is, we're talking about the slope being negative. The slope is negative till it hits this point here where it stops again. It becomes flat because it's at 0. So it's when the derivative is at 0. So the function, the original function, is flat. And then it continues to be positive, and it's going to get steeper and steeper and steeper. Now, the problem is this is only one of the potential answers we can have, because what I've just described could also happen up here. It could increase until it gets to a point where it becomes flat, where it hits at 0, the derivative is equal to 0. It starts being negative like this, till it hits this point where the derivative is 0, and then the function is going to slope up like that again, increasing as it goes. So the point is that we can have all of these different types of functions that represent, or that are represented by the derivative. So how do we differentiate between them? Well, what we're going to do is we're going to practice using this reverse differentiation, this antiderivative, and then we're going to have a look at how we can apply it later on to some problems so that we can find the exact function that we started with. Like, as in, how do we know it's this one here, or this one here, or this one here? So how do we know? So let's have a look. This example asks us to differentiate x squared. So we've got a parabola and we want to differentiate it. So if y is equal to x squared, dy dx is equal to 2x. So to find the primitive function, well, we just say to ourselves, okay, well, if my derivative is 2x, then my prime function, or primitive function, is just the original function that I had to start off with. In this case, x squared. So the primitive function of 2x is x squared, because it was the function that when we differentiate, we get 2x. Okay, well, what about this one here? We've got x squared plus 5, okay? So, same idea. Y is equal to x squared plus 5, and then dy dx is equal to 2x. Well, hang on. What's going on here? We've got the same thing as what we had before, but we started off with two different functions. So how can this be right? Well, the problem is that if we've just been told the derivative and we're wanting to find the primitive function, we can have a big range of different answers. And to represent those answers, because it's always the constant term that disappears when we're differentiating. So if I'm doing the reverse, if I'm going backwards, I'm going to end up with a potential constant term. And that constant term we're just going to call C. So I could potentially have a constant term there. And that just means that when I find the primitive, so this is not for the derivative, mind you, this is just for the primitive. So the primitive function of 2x is, and so it's this x squared, because x squared is what could have potentially turned into 2x, but there could have also been a constant term, because the constant term would disappear when we've been given our x squared value. Okay? So the primitive function of 2x is x squared plus some constant value. And so this is the same for the case up here too. The primitive of 2x is x squared plus potentially some constant. And so again, we can see this for part C. If we have a look, y is equal to x squared minus 3. So that means that the derivative of this is equal to 2x. So if I want to find the primitive function of 2x, okay, we're going back in reverse order. So I'm starting at 2x. The primitive is x squared plus some constant, because we don't know what this value is. It could be a range of different things. So we're just going to placeholder with a c. Now, some of you might be thinking, well, why is it plus c? Why is it not minus c? Well, if it's minus c, then that just means our constant term could potentially be the negative as well. So you'd end up with minus c, and it just cancels out anyway. So just having plus c, it's just a consistent way to do it. So as it says down here, 2x has many different primitive functions, and in general we would say that the primitive of 2x is x squared plus some constant term, because as I said, we don't know if it had a constant term to begin with, if the only indication that we know is that the derivative, or the function that we want to find the primitive of, is just 2x. Alright, well, let's have a look at some other examples. So find the primitive of function x. Okay. Well, if I've just been given function x, I need to think about, well, what would have differentiated to get me a solution of x? What would have I needed to begin with to get me a derivative of just x? Now, hopefully you would have realized, well, if I have any sort of x squared function, any side of x squared function, that would give me two lots of the x value, okay? But the issue is, I don't want 2x. What I want is I just want this x part here, this x component. Okay, I just want this x component. So what do I need to do to this 2x? Okay, what do I need to do to this 2x to just get the x by itself? Well, if I multiply this by a half, okay, well that just gives me x. But it means that I needed to start this side, the right-hand side, I needed to originally have the half on that side as well. So this side here is a half x squared. So therefore, the primitive function of x is half x squared, because the 2 comes down. If I was to differentiate a half x squared, the 2 would come down, 2 times a half, and then x to the power of 2 minus 1, because we subtract 1, and that gives us our answer. But remember, the primitive function isn't just that value, because there could potentially be a constant term there. So if I had a half x squared plus 10, okay, and I differentiated that, that would just give me x as well. Just like a half x squared minus 5 would also just give me x as my derivative. Alright, well, what about part B? So find the primitive function of x squared. So what function, when I differentiate it, gives me an x squared term? Well, same idea. It's going to be x cubed. So x cubed is the function that when I differentiate it, I get x squared. And in fact, what I would get is I would get 3x squared. But just like before, I don't want 3x squared, I want x squared. So what do I need to do to 3x squared to turn it into x squared? Well, hopefully realize by timesing it by a third, and doing that on both sides would mean that the function, the primitive function of a third x cubed plus some constant would give me the primitive of x squared. Okay, so third x cubed plus c. Alright, now what about x cubed? Okay, well, what can we do with this? Well, same idea. X to the power of 4 would give me 4x cubed, okay? So, same idea. What do I need to do to 4x cubed to just get x cubed? Well, we're going to times it by a quarter. And we'll do that to both sides. Just like before, we'll get that the primitive function is quarter x to the power of 4 plus some constant term c. Okay, so those are the ways we can think about doing finding the primitive function. What do I need to turn it into the thing that I want? Okay, what would I have originally needed? Now, that's all fun and games, but let's generalize this, okay? Let's do it for any power event, okay? So if dy dx, if the derivative, okay, if the derivative is x to the power of n, so x to the power of 5, x to the power of 10, x to the power of 100, then the original function, the primitive function, what we're going to do is we're going to add 1 to the power and then divide it by the new power, and then of course add on a c. Okay, example 4 is asking us, well, we've got dy dx is equal to 6x squared plus 8x. So we've got the derivative of the function. And it's saying, well, if the curve, the original curve, passes through 1 minus 3, what is the curve? What's the original curve? So what we're going to do is we're going to move away from finding this plus c, and we're going to actually find what it is. So we're not just writing the plus c on, we're actually going to find what that value is. So let's do it. Let's have a crack. So dy dx is equal to 6x squared plus 8x. Now what we're going to do is we're going to use this new formula that we've learnt up here. And it says that if I've got a derivative that's equal to x to the power of n, what I'm going to do is I'm going to add 1 to the power and divide by the new power. So let's have a look. So y is going to be equal to, so have a look at the first one. We've got 6x squared. Now I'm going to add 1 to the power, and I'm going to divide it by that new power. So 2 plus 1 is equal to 3. Plus, we've got 8x. Now, the power for x is 1, because x to the power of 1 is just equal to x. We're going to add 1 to it. So we've got x to the power of 1 plus 1, which is 2. So we're going to divide it by 2. So this is the same as 6x to the power of 3 divided by 3 plus 8x squared divided by 2. And of course, we can simplify this one step further and get 2x cubed plus 4x squared. And of course, we can't forget that constant term, okay, that plus c on the end. Well, now let's find what that constant term is so we can find the exact function. Because if we're adding a constant term, remember, we're just adding a constant term to the end of a function just shifts it up and down. So we want to work out, well, where specifically is this function? So let's find out. We've been told that we've got the point 1 minus 3. This particular point will go through the function, the original function. Well, my original function is here, right? The only thing that's missing from this original function is the fact that I am missing what the constant term is. So what we're going to do is we're going to substitute 1 and minus 3 into their respective parts. So y is equal to minus 3, so we have minus 3 is equal to 2 lots of 1 cubed plus 4 lots of 1 squared plus some constant term c. Minus 3 is equal to 2 plus 4 plus c minus 3 is equal to 6 plus c, so c must be equal to negative a half. So if c is equal to negative half, that means that the function that goes through the point 1 minus 3 that has derivative 6x squared plus 8x must have been 2x cubed plus 4x squared minus a half. And see, this is an example where we're going to get a negative, sorry. And so that guy there is our solution. Okay? I probably shouldn't write a line under there because it makes me look like I'm about to write a fraction. But that is our solution there. Alright, last example that we're going to look at. So if we have that the second derivative is equal to 6x plus 2, and that the first derivative at the value of 1 is equal to the original function when f is equal to negative 2, or when x is equal to negative 2, and they're both equal to 0, what we're going to do is we're going to find f of 3. Well, let's get into it. So if we know the second derivative, the first derivative is just the primitive function, it's just the antiderivative of the second derivative. So if I've got 6x plus 2, then we go through the motions and we do the same thing. So 6x to the power of 1 plus 1 makes 6x to the power of 2, divided by the new power, plus, now 2 is just a constant term, so how do I change a constant term? Or what would have I differentiated to get the constant term? Well, that just is just an x, okay? So the constant terms are really easy. You just put an x on the end, and that happens every single time. Plus c. Okay? Now, before we can do the second part, we actually need to work out what this plus c is, because if I now try and do the antiderivative, c is a constant term, I would end up with cx plus, and then some other constant. So I'd end up with these two values that I don't know. So what we'll do is we'll find c first. And we've been told that we've been told that the first derivative at 1 is equal to 0. That means that when I substitute 1 into this, the whole thing will be equal to 0. So let's substitute 1 into this, okay, and make the function equal to 0. So we get 6 times 1 squared over 2 is just equal to 3, which I could have probably simplified before that, but that's okay, plus 2 plus c. And so therefore c must be equal to minus 5. So add 3 and 2 together and move it to the other side. So that means the first part, or the first derivative, is equal to, so we'll simplify it at this step, 3x squared plus 2x minus 5. Okay, let's continue back up here. Now we've got the first derivative. What we're going to do is we need to find the original function. Okay, so the primitive of the first derivative. So same idea again. Okay, 3x squared. Okay, so the original function, I take 3x squared. Okay, I add 1 to the power to get 3x cubed, divide it by the new power. Plus 2x, add 1 to the power, so 1 plus 1 is 2, divide it by the new power, which is 2. Minus 5, 5 is just a constant term, so we can just tack an x on the end. And then plus some other constant term. Now we use d for this one, just to mix it up a bit, so that we know it's different from this one, because it's not going to be the same value. So we'll choose a different letter, just because it might be a different answer or a different value. Alright, let's just simplify this a bit. 3 divided by 3 is equal to 1, so it becomes x cubed. 2 divided by 2 is equal to 1, so that becomes x squared, minus 5x, plus some constant term d. And this is what f of x is equal to. Now, same idea as before, because we've been told that f of minus 2, so when I substitute minus 2 into this, the solution will also be equal to 0. So, when I substitute minus 2 into the right-hand side, it should be equal to 0. Now simplifying the right-hand side, minus 2 cubed is equal to minus 8. Minus 2 squared is equal to a positive 4. Minus 5 times minus 2 is a positive 10. Plus our constant term d this time, or c2 if you prefer, 10 minus 8 is 2, plus 4 is 6, so 0 is equal to 6 plus d, and so therefore d must be equal to negative 6. So that means that the original function, f of x, is equal to x cubed plus x squared minus 5x minus 6. Now finally, we haven't actually answered the question, because the question that we've been trying to answer is to find what f of 3 is. Well, we know what f of x is now, so what we can do is we can find f of 3 by substituting 3 into this equation. So 3 cubed plus 3 squared minus 5, keep it consistent, minus 5 lots of 3, minus 6. So we get 27 plus 9 minus 15 minus 6. Doing some quick maths in my head, 27 plus 9 makes 36. Take the 6 off to get 30, and take 15 off to get 15. I'm hoping that is right, but that is how we find that solution.